Okay, let's start. As I said before, this second one is more about what I do in my everyday work, but I will try to give you an overview of some new programming paradigms like task-based programming, and I hope you will find out some ideas of how C++ can be used in HPC, which is the case of DLA Future. And I will present also a bit the underlying library that we use for task-based programming. Okay, DLA Future. It is more or less an acronym for Distributed Linear Algebra with Futures. And the field is the linear algebra, and since 1995 the linear algebra world has been in HPC has been dominated by Scalapac, but this Scalapac library, being so, let's say, old, did not evolve with the supercomputers architectures, and so new programming paradigms are necessary, and with DLA Future we are trying to do exactly this. In fact, DLA Future uses a task-based approach. I don't know if any one of you already know what task-based approach is, but you can think of a generic algorithm, and inside this algorithm, you can identify some units of computation, and you can define some kind of dependency on these, and you can run them in parallel or concurrently. The task-based approach requires, let's say, it's still not available directly from the language, and it requires an underlying library, which in our case is HPX, to be able to deal with this new approach. What is HPX? This is a screenshot from their GitHub page. HPX is partially developed also from a team at CSCS. We are part of the core contributors of HPX. Not me directly, but we work in contact with them, and there is a big effort in supporting HPX from CSCS. And HPX is a C++ standard library. I highlighted for concurrency and parallelism, which is not the same thing. I don't know if you know the difference, but concurrency and parallelism somehow are the same thing, but at the same time, not the same one. And concurrency means that the different threads running on for an algorithm, they are dependent somehow between them, in the sense that we may have a dependency on another task. We have to wait for it. Well, with the parallelism, it's the, let's say, the parallel for. So we can do it in parallel, the same thing, without any kind of synchronization between the running threads. This is, let's say, a trivial definition. But the second thing I highlighted from their description is that it implements all the corresponding facilities as defined by the C++ standard. So it is important because it sticks to the C++ standard. We are not taking another route from the C++ standard. With HPX, we're still working under the C++ standard. And this is really valuable. And even more valuable is that HPX, the third highlight in Bordeaux, is that HPX implement functionalities proposed as part of the ongoing C++ standardization process. So we get through HPX things that are not still in the standard, but we can test them, and we can also somehow help steering the standardization process, because we have use cases for it. So it's an effort that HPX tries to keep up with the standard, but it also gets feedbacks from use cases of applications of the proposals. So it's really important, and it allows us as the DLA Future team to keep up with the modern things. As I said, HPX is something needed because the language doesn't provide all the things we need for task-based programming. And we can think about HPX like I tried to depict here in the diagram. Yeah. Sure. Artmut is in. Yeah, I already had contact with Artmut. He's a really great developer. Yeah. Yes, I suggest to give a look at HPX, even just to get an idea of what it is, because it may be really helpful, and it may give you some idea of how you can program differently, and in a lot of fields, this task-based programming can be applied. I know that not everyone is agreeing with this statement, but in our case, I will show you later, it is a really helpful way of thinking and of programming. About HPX, an overview. HPX has a runtime, so there is a manager that, let's say, inside the HPX runtime, it has to deal with the actual compute resources, being them CPU or GPUs, which you can see depicted on the right. And the work that it is that will run on these computing resources, the work is fetched from a DAG. From the DAG, which is a directed acyclic graph, you get the tasks that the user defines, and we are going to see how the user can define them. And in the DAG, you define dependencies between the different tasks. And as soon as a dependency is satisfied, the HPX runtimes notify the new task to a queue. So it fetches from the DAG and it puts it in a queue. And then as soon as it is possible, the queue will give the actual work to do to the computing resource. It is a very, very, very simplification of how HPX works. There are a lot of things and a lot of changing things. And you can have high priority queues, low priority queues. You can have queues that steal from other queues. You can do whatever you want. The main point about HPX from the user point of view is the DAG. Inside the DAG, you can say, I want this task to depend on these other tasks, and I want to execute this task on a GPU, while this other task on a CPU. And so the user point of view is the DAG. You have to define the DAG. Let's see an example of what a task is. Well, a very trivial example. Unfortunately, I think you're not able to read what it is written in the snippet. I have to check better next time to make them more readable. But the thing that I want to note here is that at the first line, we have a generic function task where we don't have the implementation. We know it is a task function that gets an input, an int parameter, and it returns a float. And when we call it with a standard async, we pass the function name and the parameter, and we don't get the float. We get a future float. And this is a very important thing, because you don't really get the result. In fact, if you see at the next line, you have to wait for the result, and then you can get the result in the last line. What is happening? Well, the above snippet is more or less depicted as a timeline graph on the bottom. When you call async, you may start this task function running on another thread, so another timeline. Okay. On the left side, where you started where you launched the async, you keep just the result, but the result is not the result value. It's just a handle to keep track of the future result that you will get from the execution of task. And so you can wait for the result, or you can do whatever you want. But before you are able to get the result, you have to wait for it, and then you can get it. It's not exactly true, because the get call itself waits. If you just call get, if the result is not ready, it becomes a blocking call and it waits. This is a very general idea, but what I want to highlight here is the future object. The future object is implemented like this. It's, let's say, this is how it works, not how it is implemented. There is a shared state in the middle, let's say between the caller and the callee. And this shared state is used from 2 points of view. There is the producer on the right, the one that we've seen before on the right, that can set the value as soon as it is ready. On the left, we have the user, the one that wants the future result, that can call get on the shared state and get the actual value. Again, on the bottom snippet, I tried to give you an idea of how the mechanism works. It is a very simple and trivial example, but it gives you an idea of the relationship between promise and futures, because the promise on the right is the promise of a value, of a future result, while the future is the handle to the future result that will be set by the promise. Just trying to follow the snippet, on line 4, we define a promise of an int. So we are promising on that line that promise will store an int. So the shared state will store an int. On the next line, line 5, we can create a future by asking the promise to get the future with the method getFuture. And this gives us the access, the handle, the future, to the same shared state. So they are, this promise and future, they are strictly in a relationship, because they actually points to the same shared state. It looks like more or less what we saw before with smart pointers, but it is a bit different. When we set the promise with the value, the actual value, the line 7, at that point, the shared state is populated with the actual value. In that exact moment, the future can get the value without practically waiting, because the value is ready. Again, this is a trivial example, but if you think, try thinking about this example applied to different threads, you may have a thread which stores the promise, and a thread that keeps the handle, so the future, and you can play with them, because each thread may have its life, and from the future point of view, you just have to do whatever you want and then wait for the result. From the promise point of view, you can set the result as soon as you have it ready. And so this is the promise and future mechanism, how it works. We are going to see more or less how it can be applied to a use case in DLAF future in a moment. Okay, just like future exists, also shared future exists. As I said, it mimics a bit the things we had with smart pointers. It is the equivalent some way of the shared pointer. We have the shared state. We may have different shared futures that share the same shared state. And there is always one promise, because the value can be set just by one. We can just have multiple handles to the same resource. Okay, about future and shared future, what are the differences? Okay, the future, like unique pointer, because it is, we are going on with this parallelism between future and future and promise in smart pointers. The future is not copyable because it's unique ownership, and this means that as soon as we get the resource from the result, the resource from the result future, the future is not valid anymore, because we get out the ownership of the result. In fact, if you look at the green part of the two snippets, you can see that in the middle there is the retrieving part of the value. On the left, we have the future, and from a future, you get the actual value by copy. While on the right, with the shared future, you get a const ref. And this has implications, because with the const ref, you're not taking the ownership, because there may be other shared future around referring to the exactly same shared state. So you just get a reference to it. While with the on the left, with the future, you actually get the object inside the shared state. And as you may see, if both of them on left and right, there is an assertion that both are valid, after getting the result, the left one is not valid anymore, the future. Valid means, does the future point to a valid shared state? So a shared state that has some object or a promise that it is going to populate that shared object. And so these are the main differences. And you can see also the parallelism with the smart pointers. I highlighted also the shared future thing with the underlined red line, because as we've seen, for smart pointers, it is possible to get a shared future from a future, and it is a unique pointer. It is possible to get a shared pointer from a unique pointer. The same thing happens for the futures. You can get a shared future from a future. Indeed, the standard async call returns a future. Like we said, it is always better if you don't know if it is a unique or shared ownership. Standard async just returns a unique ownership, so it returns a future. Okay. In fact, it is assigned easily on the left. On the right, we are not seeing it, but it is underlying. There is somehow a move from a future to a shared future. Okay, I have to speed up a bit, but let's see how the HPX things works. We said the user point, from the user point of view, there is mainly to deal with the DAG. We can see the future as a task, let's say a resulting value with just a single outgoing arrow. A shared future, a task with multiple outgoing arrows. This is because the shared future, differently from the future is unique. So just one unique ownership. So just one can get the value. While with shared future, we can get more. In HPX, differently from the standard, there are also some helpers function, some extensions, as we said, and one of them is the .then. So we can attach to a future, another task, and in the DAG it can be represented with it, with the DAG that I presented above, with just two simple results connected by a single dot. And another thing is about shared future. They still have the .then, but there is a small difference here because, well, I unfortunately I don't have enough time, but we may get back on this in the Q&A session if you want to get a more insight on about HPX. But you can have the .then also with the shared features. And then there is the data flow, which is somehow the opposite operation on DAG of the .then, and it allows you to merge different dependencies. Or better, you can have a task dependent from multiple tasks. So with this operation, we define the atomic operations on the DAG, and with this DAG, you are not working in terms of fork and joins. You are defining dependencies over tasks. It has to be clear. The DAG doesn't represent a simple fork and join. It represents dependencies over the tasks. Let's see it applied to DLA future. I will go very quickly, but I hope that you can follow me. DLA future. DLA future, D stands for distributed, so it implies communication. And for us, communication means MPI. And this is because we want to replace Calapac in existing Fortran C, C++ application, and MPI is standard. But it poses a few challenges. The main challenge with communication is the communication order. Since tasks can be executed in whatever order the HPX runtime prefers, just let's say respecting the dependencies, we may end up with out of order communication. So this implies that we send from one rank. For example, in this picture, the left one is the 0 rank. The task may execute the third one instead of the first one in order, and the other one will get the wrong result. It will receive the wrong data. And so how we deal with that? We implemented the pipeline, and the pipeline is about adding a fictitious dependencies that describe the order requirement. And how we implemented that? Since the data can be different from communication to communication, because the communication is by definition is done for communicating data, the only handle we have for adding these dependencies is the communicator. And actually, it is what MPI doesn't manage, because MPI allows you to communicate independently on different communicators, but on the same communicator, you have to keep them in order. And with collectives, you don't have tags, so you cannot impose an order in other ways. So we decided to implement a pipeline, and we serialized the access to the communicator. The pipeline is made of two objects. There is a promise guard, and there is the pipeline itself. The promise guard is just an object that on destruction releases a promise. So it sets a promise. And you can get access to the actual resource through the ref method. The pipeline stores this pipeline of promise guards, and the actual work is inside this this green box. Unfortunately, we don't have enough time because it will take time to describe in all the details this one. But the pipeline for the promise guard allows you to release to the user a future result, so a future to a communicator. And as soon as the communicator will be used by any task, when the task finishes, the promise guard will be destroyed. And destroying a promise guard will mean setting the promise, and the promise will release the next promise guard. So we get a chain of promise guards, and each promise guard points exactly to the same communicator, but they are released once per time. and in series. And so we get a dependencies over the different time of the communicator. And so we are able to impose this order. It's just a partial solution because, as you can see on the left, we may have 5 green communication that can run in parallel, but since they can run out of order, by imposing the fictitious dependencies with the pipeline, it means that let's say the bottom one cannot run in parallel, and so it has to run as last. And even if it was able to run just because the data was already there, it cannot run because it doesn't have the communicator, because the communicator has to be released by the first 4. And so it has some implication on the performance side, but it allows us to work also with asynchronous communication in MPI. And just a few words about the algorithms. In DLA Future, we use the tiled version of algorithms. And in this way, we are able to have a more fine-grained parallelism and control over the computation units of the algorithm. And it is some also called data-driven task-based implementation. And since the work is based on tiles, of unit of computation of tiles, we opted for organizing the matrix in tiles. So the data is organized in tiles, and these tiles also manages the dependencies of the tasks. So each tile may have its own let's say sequence of shared and future and shared future, so read-only and read-write access, and the mixing of different timelines from each tile ends up in the DAG, mixing up, and it describes the algorithm. It allows us to run the algorithms like Cholesky or the full eigensolver soon, trying to fully use the resource available, because even if we define the dependencies, we are not defining the order of execution. So the HPX runtime is able to realize when a dependency is ready, and by consequence, it will run the task. It seems like when you see a computation from DLA Future, you are not anymore able to realize the order of execution of the algorithm, because it gets, let's say, interleaved by other things, because you can have also interleaved the execution of other algorithms. But this is what allows you to fill the gaps between different computation with other things to do, and maybe from the same algorithm. And okay, last slide. I asked Michael Simbari, which is my colleague from CSCS that works on HPX, and about the future of futures, because it seems that the standard committee is changing his mind about futures, because there are different downsides, and the new let's say the new concept introduced will be sender and receiver. It is quite similar, but it removes some constraints, and they seem very promising. I just have scratched the surface of this new argument, but if you want to get more details, you can give a look at the actual proposal to the standard, which you can see at the link wg21.link. And if you want an explanation, because maybe the proposal is not so straightforward, you can have a look at the YouTube video by Eric Niebler, which has been cited by Anton already today. And that's it.